Welcome back again. This is the last section of Chapter 7. If you've been hanging with me the whole time, congratulations, you have almost made it. I think I'm going to do purple this time. Did that do red? I wanted purple. We're going to talk about properties of solutions. And if you've seen solutions, you know they can be, some things can be thick. Like a solution of honey is going to be really thick, but a saltwater solution is going to be really thin. Sometimes they have colors. Sometimes you can put things in them to have a higher boiling point or something like that. And so there are things that you can do to manipulate these solutions and change those properties. So most solutions are going to be transparent. They don't separate. They have small particles or molecules or ions, but you can't filter them, right? So you can't filter them. And so these solutions pretty much stay intact unless you go to extremes. Colloids, however, have medium-sized particles. They still can't be filtered, but they can be separated by what's called a semi-permeable membrane. Okay, and if you recall, that's like what a cell wall is made of. And so it's semi-permeable because some things can go through and other things cannot. And so it is selective in how it can allow those things to happen. Colloids you see a lot in nature. And so you have water that are components of a lot of different natural substances. Just like us, we're made, a lot of our liquid is water, right? And so you see colloids. You also can see suspensions. Suspensions have very large particles and they settle out, and that is like if you put them in a container and they're all mixed up, if you leave them and let them sit for a while, you're gonna have solids in the bottom eventually. Okay, and so that's a suspension that's settled out. You can also filter those out because these particles are large enough that filter paper will stop them. If you want them to stay in solution, you're going to have to stir them. Okay, not so with colloids. Examples: blood platelets, muddy water, calamine lotion, if you've ever seen that, to put on for poison ivy and things like that. Okay, so these comparisons, a solution, okay, the particles don't settle. They cannot be separated by filtering or by a semi-permeable membrane, and they have small particles. Colloids have larger particles. They still don't settle, but you can separate them by semi-permeable membranes, but you still can't filter them. And then suspensions are very large particles that will settle out, and you can filter those to remove the materials. Okay, and so they're just kind of showing you how the suspension will settle out. You can separate them by filtering. You can separate with semi-permeable membranes, such as dialysis tubing. Alright, so a mixture that has solute particles that do not settle but are too large to pass through a semi-permeable membrane is what? A solution, a colloid, or a solution. Or suspension, sorry. Right, a colloid. Okay, because they won't pass through that semi-permeable membrane. Colligative properties are properties that depend on how many particles you have in the solution. Colligative properties include your freezing point depression or freezing point lowering, or your boiling point elevation. What's that mean? That means you can take a solution and you can add something to it, and you can either lower the freezing point or increase the boiling point because you need to use it for something. Ethylene glycol, for example, is something that you put in your radiator instead of just putting straight water because it lowers the freezing point and it increases the boiling point. So it helps in the wintertime or the summertime in your radiator to keep you from overheating your engine. These solute particles basically disrupt any type of salting out or the salts in there forming and coming out of solution, and so they lower the freezing point. Electrolytes break up these ions in solution, as we've already seen, and when they do that, they increase the number of particles. So when you add salt to something, you are going to lower the freezing point. You can also elevate the boiling point. Okay, so calcium chloride can be used, regular salt can be used, and what are they doing here? They're salting the road. So if they have lowered the freezing point, that means it's going to have to get colder in order for the ground to freeze. Osmosis is something else that we see with solutions. The water flows from low solute to high solute concentration. That's the opposite from solutes. If you remember, solutes go from high down the concentration gradient to low. But with water, water flows from low solute concentration to higher solute concentration. Because what we're trying to do is we're trying to dilute it so that they will be the same concentration eventually. So the level of the solution with the higher solute will rise until the concentrations of both of them will be equal. This happens a lot of times in these semi-permeable membranes because sucrose is too big to pass through this membrane, and so the water will have to pass in order to try to dilute this, and so the water would move this way and increase the level because it's trying to make both sides of that membrane be the same, because it's an equilibrium, and it is just a natural order of things. So what is really pushing this, if you'll forgive the pun, is the osmotic pressure. And the more solute particles you have in a solution, the more osmotic pressure you have. And osmotic pressure is equal to the pressure that would push against and stop the flow of water coming into the concentrated solution. So the more particles you have, the higher the osmotic pressure is. Okay? A semi-permeable membrane separates 10% sucrose solution from a 5% sucrose solution. So the solution, which one of them, A or B? A is a 5%, and the other is a colloid. So which solution has the greater osmotic pressure? Water initially flows from where to where? From the 5% to the 10%? And which level would be lower? So solution A, okay, would have a greater osmotic pressure. Water would flow from, and they're talking about between A and B. Water would flow from B, because it's a colloid, into A, because it can go through, because it's a solution. Level of the solution B then would be lowered because it has done what? Moved to the side with A. Osmotic pressure is really important in red blood cells. Red blood cells have cell membranes that are semi-permeable, and they maintain an osmotic pressure. And if that osmotic pressure changes very much, it can damage red blood cells. And most of us know red blood cells are necessary to carry oxygen, and if our red blood cells become damaged and we don't get oxygen, then we're going to be tired, fatigued, our processes will slow down, and it could end up dying. And so it's important that we maintain an equal flow of water between red blood cells and the surrounding tissue. So if you have the same concentration outside the red blood cells as you do inside the red blood cells, then you have the same osmotic pressure, okay? And we call that isotonic, iso for same, okay? So the pressure outside is the same as the pressure inside. And the typical solutions that you can see used is going to be a 5% glucose or the 0.9% sodium chloride, because those are isotonic to our tissue. So if they give us that, then that's not going to mess anything up. So in an isotonic solution, your red blood cells are going to be happy. In a hypotonic solution, that means that you have a lower osmotic pressure outside than you do inside. Okay, so basically what that means is, if you're looking at the red blood cell, you have some particles in here and you have fewer outside. And so remember that what the water does is, if the water is if the solutes can't move, the water's going to move. So if you've got a lower concentration out here, water's going to move in here to try to dilute the higher concentration. And these guys are fragile, okay? So if that water keeps coming in here, eventually what's going to happen is you're going to have a blowout, and it can literally burst that red blood cell. That's called hemolysis. Lysis means blowing up, basically, or destroying. And so in a hypotonic solution, so that's why we give, like if we give solutions to somebody, we give that normal saline solution, because that's the same kind of concentration that we have in our fluids in our body. If we gave distilled water, that would be hypotonic. And if we gave a lot of distilled water directly into the bloodstream, we would be blowing up our red blood cells. So that's why we give normal saline. A hypertonic solution would mean that you've got a few inside the red blood cell, and then you got a lot of this solute outside. So again, remember, water is going to go from low solute concentration to high, so the water is going to come out. Well, this is a little bitty red blood cell, and this is a really big environment, and so its water would continue trying to dilute this. And so what would happen would be that it would keep doing it till it didn't have any more water inside here, and it would cause it to basically implode and shrink and stick to itself. And so that is called crenation, where your red blood cells are going to shrink, and again, they're not going to be able to do their job, just like, you know, the ones that blew up. So crenation happens in this hypertonic solution, because it causes these red blood cells to sink and crenate, and so they literally can't do their job anymore. Why do we do dialysis? Well, people go on dialysis because their kidneys aren't working anymore, or they're very low functioning. And so in dialysis, what happens is we use that semi-permeable membrane. It's an artificial membrane in a machine at this time, and we push that fluid through there, basically your plasma, and the solvent, the water, and the small solutes are going to go through that membrane. The large particles are going to be retained, and so your waste particles such as urea, ammonia, that kind of thing, from the blood are removed by filtering this out, and that they call that hemodialysis. And so dialysis uses this same type of procedure, where you have a semi-permeable membrane and you develop all these toxins, right? And so what you're going to do is the small things are going to go through, okay, like, you know, the little molecules of, you know, sodium, some of your ions. But these big toxin molecules are going to get trapped behind this filter in the dialysis machine. And so basically it's filtering the blood and cleaning it out, just like happens in the kidneys. So indicate which of these solutions is isotonic, hypotonic, or hypertonic. And it's talking about in the body. We said that sodium chloride in the body is about 0.9%. So this one is higher, so that's why it's hypertonic. 1% glucose solution, we're about 2%. And so that would be hypotonic. 0.5 sodium chloride would be hypotonic, again, because we're about 0.9%. Sorry, it's 5%. And 5% glucose is what we are. So that would be isotonic. So predict what would happen to the red blood cells if we did the following. Okay, we said this is isotonic. That would be hypotonic. This would be hypotonic, and this would be hypertonic. So if our red blood cells are put in a solution of 5% glucose, they should be okay, right? Because that's iso. 1% glucose solution is going to be hypo. So the water would come in, right? So the water comes in, then that should be hemolysis. This is again hypo, because we should be 0.9%, and so hemolysis. And then 2% sodium chloride, which is much higher, so we should crenate. So let's see. Yep, we did. Okay. Go back and review this if you're not getting it, because this is important to understand. And on that note, congratulations. You have actually come to the end of Chapter 7, Properties of Solution. And we are done with that. So hopefully you've gotten something out of these, and it will help you study and make great grades.